Hello everybody, welcome to the first lesson of week 4 of distance learning. We're starting a new unit today. The unit is called Work, Energy, and Power. It's all in chapter 5 of the textbook. So you can do some reading there if you would like a different way of explaining the material. All right, so the topic for this week is work. Work, it's a common word used every day. It's got a lot of different meanings, but in physics, it has a very specific meaning, and that's my goal for this week, is to try to teach you what that specific physics meaning of the word work is. All right, work has to do with forces and objects again. So this is actually a continuation of Unit 2, pretty much, and Unit 1 as well. So the first 3 units of this course all kind of run together. Units 4 and 5 will be different, but yeah, we're still talking about forces and objects. So here's a couple of statements that you might have heard from the previous unit. All right, so I call it old language. So in the past, we've said that a force acts on an object. Okay, a force acts on an object. So gravity acts on an object downwards. Normal force acts on an object perpendicular to the surface. An applied force acts on an object or pushes on an object. Okay, so we've used that language before. We've also saw how a net force can cause an acceleration. That's Newton's first and second law, really. If you have a net force on an object, it can cause an acceleration. So a force acts on an object. Forces cause accelerations on an object. And now the third thing we're going to start saying, so this is new language, is that a force does work on an object. Okay, a force can act on an object, a force can cause an acceleration on an object, and now we're going to start saying that a force does work on an object. So you're going to start getting used to that language and saying sentences like that. We'll get more specific as the unit goes on. So this is the definition of work. So this slide here is kind of giving you the big picture. Work is defined as the dot product of a force acting on an object with, and the displacement the object moves. So work is defined as the dot product of force with displacement, basically. That's written out like this. So W is, capital W is the symbol for work, and F and delta D with vectors should be familiar to you. Now this is new. This symbol right here in the middle, it's a dot. And you may think, oh, dot just means multiply. I just multiply the two numbers together, which is correct. However, when you put the dot in between two vectors, because these are two vectors, it means a little bit more than just multiplying them together. And I'm going to explain what that means in the future slides. But for now, this is the formula for work. Our new word, our new topic has this formula. It's the dot product between force and displacement. Another way to say this is force dot displacement, or F dot D for short. Now, work is a scalar quantity, and that may seem strange to you because these two are vectors and we're kind of multiplying them together. So shouldn't the answer also be a vector? Well, it's actually not. All right, so the dot product actually gives you a scalar at the end of the day, and that's why this W does not have an arrow over top of it. So work is a scalar quantity, this new idea of work. And then it's got units. So the SI units, or the standard units of work, are called joules. That's named after a scientist who did a lot of work with energy, which is the main thing we're talking about this unit, is energy. Okay, so joule is a capital J. So W is measured in joules, or J. Now, since work equals force times distance, or displacement, The units of force are newtons, and the units of displacement are meters. So that means that 1 joule, which is the unit for work, is actually the same thing as 1 Newton meter. 1 joule is the same thing as 1 Newton meter. All right, but we're mostly going to just use joules for the units for work. All right, so now I'm going to try to explain what this dot product thing is all about. What is the dot product? So first I'll write out the definition in words. The dot product of two vectors is the product of their magnitudes multiplied by the cosine of the angle between them when drawn tail to tail. So the dot product of two vectors, you just multiply the two numbers together. That's what the product of their magnitudes means. So that seems like it's regular multiplication. But the extra detail is that you also have to multiply it by the cosine of the angle between them when drawn tail to tail. So this is what it looks like in picture form. If you have two vectors, so in our case, work equals force dot displacement. So the vectors would be force and displacement. If you draw them tail to tail, okay, so the beginnings of the vectors are touching. And then you measure what the angle is that they make together. I'm going to call that theta. Then the formula for the dot product between these two vectors is you just multiply how big they are in magnitude, and then multiply it also by the cosine of the angle that you found by drawing them tail to tail. And that's what the dot product is, and that's the formula for work. In a future video, I'll explain why it's cosine theta. Why don't they use sine theta or tan theta? It seemed pretty random that they chose cosine theta, but there is a reason for that. I'll try to remember to share that reason with you in a future video. So as an example, a box is pulled 10 meters forward across the floor by a rope with tension 15 newtons, angled 60 degrees above the horizontal. Determine the work done by tension. So there's that language I talked about at the beginning. Work is something that's done by a force. A force does work on an object. So in this case, the tension force does work on this box. This tension force does work on this box. So to solve this, the first thing I would do is I would draw the two vectors tail to tail. So I would draw vector for displacement forward, and then tail to tail to that I would draw a second vector that's 60 degrees to that vector, just like this. So this is the direction of the displacement. I just drew it horizontally, and then this would be the direction of the force. It says it's 60 degrees above the horizontal, and I drew the tails together. Now, it's important to keep in mind that how long I draw the arrows does not matter at all, because I'm not going to compare how long they are, because they're different types of things. One of them is a force, it's measured in newtons. The other one's in meters, it's a displacement. So they're completely different types of quantities. We're not going to compare the magnitudes. I only drew this picture, the only reason I drew this picture is to figure out this angle. And it's 60 degrees. So now to calculate the work, well, I write down the work formula. Work equals F dot D, which means the magnitude of F times the magnitude of D times cosine of the angle between them. And now I just fill out all three values. The force will be 15 newtons. The displacement will be 10 meters. And it'll be cosine of 60 degrees. And then I multiply that all together. I chose 60 degrees on purpose because the cosine of 60 degrees is perfectly 1/2. That makes the math a little bit easier. So when I multiply all that out, it's 75. And let's remind ourselves, what are the units of work? They're a new type of units called joules, or Newton meters, because it's 50 newtons times 10 meters. So you could also call them Newton meters. So that's a basic example there. But this lesson, I actually don't want to focus on the calculations just yet. I want to focus on the sine of work. So when you use this formula, after enough examples, you'll see that sometimes the answer is positive, sometimes the answer is negative, and sometimes the answer is 0. Now, I actually want you to be able to predict which of those three it's going to be before you even plug in any numbers. Okay, and I made this table to try to help you do that. So I'll start with when the answer is going to be 0. 0 work is going to be done when? Well, when any one of these three is 0. This is all multiplied together, so 0 times anything is 0. So if the object doesn't move, that means the displacement's 0, then the answer is going to be 0. Furthermore, if the force is perpendicular to the motion, so the force and the displacement are 90 degrees to each other, then theta, the angle, will be 90 degrees. And if you type in cosine of 90 degrees in your calculator, you're going to find that that equals 0. Okay, so those are two situations when the answer is going to be 0. And I just wrote a couple of examples there. You can read on your own. When will the answer for work be positive? The answer for work is going to be positive when the force is in the same direction or partially in the same direction as the motion. So if I apply a force that way to an object, and the object actually moves that way, then my applied force will do positive work on the object. In the previous example, the tension pulled the box in not completely the same direction, but both of these arrows are at least kind of pointing towards the right. So the answer should be positive if they're at least partially in that same direction. And when we put in numbers, we did get a positive answer. Finally, the answer will be negative if the force and the force is in the opposite direction or partially in the opposite direction as the motion. So if a box slides to the right, well, then friction will be resisting that. Friction will be to the left. So if the object's moving one way but the force is pointing the other way, the answer to work is going to end up being negative. So got about a minute and a half left of film time. So I'll talk about a few quick examples of when it's positive, negative, or 0. And then I'll get you to do a Google form for you to practice yourself. So let's see how many I can get done. Start with tension. So if this pop bottle is pulled upwards and my tension is also upwards, well, then tension is doing positive work on the pop bottle. However, if the object is moving down, but my tension is still upwards, then they're in opposite directions. Okay, the tension is in the opposite direction of the pop bottle, so that would be negative work. Now here's the tricky one for tension. If the pop bottle is swinging back and forth, this is a tricky one, you'll find that the rope is always 90 degrees to the velocity of the bottle. The rope's always 90 degrees to the velocity of the bottle. So that's a case when they're perpendicular to each other, and that's 0 work. If I allow an object to slide down a ramp, slides down a ramp, well, it moves down at an angle. So gravity is straight downwards, so they're sort of in the same direction. They're both kind of downwards. So gravity would do positive work on the Jell-O box. Normal force is perpendicular to it, so it does 0